honored to present Dr. Bob Howarth, the David R. Atkinson Professor of Ecology and Environmental Biology, and Faculty Fellow at the Atkinson Center for a Sustainable Future at Cornell University. Another very learned man, and I think you'll enjoy his talk about the nitrogen aspect to cyanobacteria and harmful algal blooms. If I said that correctly.
Sounds great, thank you. Thank you for the opportunity to present to you today. It's an honor to be among people who care so much about the lake, and also with this particular group of speakers. Very much enjoyed John's talk. I agreed with everything he said. I'm going to use some of his data as well as DEC data in what I'm going to talk to you about now. I want to look more deeply into some of the nutrient aspects that John was talking about. He was concentrating mostly on phosphorus, and I'm going to talk about phosphorus, but also nitrogen, and I'm going to try to explain to you why as we move along. So let me start simply here. Phytoplankton that we're worried about are both cyanobacteria and microscopic algae. They need nutrients, nitrogen and phosphorus, in order to grow, but when those things get out of whack is when we start to have water quality problems. So that the classic view of water quality in a freshwater lake is that when you get excess nutrient inputs, we have excessive growth of the phytoplankton, eutrophication, the water turns green and cloudy. It's basically too much of a good thing, right? And this is a decades-old experiment in Ontario. If you take a lake like here where there's no nutrients, you have nice water quality. Here they've experimentally added phosphorus and they've degraded the water quality. So we've known for a long time that phosphorus is the biggest problem in terms of water quality in freshwater lakes. Nitrogen, I've worked on nitrogen for a long time, but not in lakes. Most of my work on nitrogen is in coastal oceans where water quality is controlled largely by nitrogen. Phosphorus is generally the bigger problem in freshwater lakes, but I'm here today to suggest that there's a nitrogen issue we should be paying attention to in lakes, or at least perhaps we should be. John mentioned that the phytoplankton in Owasco Lake are phosphorus limited. I completely agree with that. In almost all of the Finger Lakes, certainly Owasco, Skinny Atlas Lakes, the total amount of phytoplankton growth is determined by the amount of phosphorus that goes in. And there's classic work on that done at Cornell by PhD students, bioassays, and this is a nice figure out of the most recent DEC report, which is a great report, by the way. I'm going to show a lot of their data as well as some of John's. If you look across the Finger Lakes, with more phosphorus, we see more chlorophyll, more phytoplankton in these lakes. So phosphorus is what's controlling the overall amount of growth. That's not surprising when you look at the relative amounts of nitrogen and phosphorus. And this is a slide from one of John's reports. Just looking across several lakes here, we're looking at the inorganic phosphorus and the nitrate, which is the major form of inorganic nitrogen in the lakes. And I've just pulled out some numbers here. So we're looking at the relative amount of nitrogen to phosphorus. There are a few thousand times more nitrogen than phosphorus in these lakes. Cyanobacteria and algae use both nitrogen and phosphorus. They need about 16 times more nitrogen. So the fact that there's thousands of times more nitrogen means there's a huge surplus, and that's why phosphorus is the element that's overall controlling the growth rate. Now overall, if you were to just look at a plot like this, you'd say, and again this is from one of John's reports, you'd say that the Finger Lakes generally have very high water quality. We're looking here at the amount of chlorophyll. This is Owasco Lake over a period from 2005 to 15, Skin and Atlas. Chlorophyll is low. These are low productivity lakes. Skin and Atlas is particularly low, and I'll come back and talk about that in a minute. Phosphorus may be changing somewhat over time in the lakes, but it's not dramatic. So if you look at Owasco, we have data from the 1970s, 90s, 2000s, 2017. There might be a slight increase there, but if so, if that's real, it's small. So the phosphorus is low. It's not a dramatic increase over time. And yet, as you all know, we have these HABs problems. So the harmful algal blooms are occurring. If we look at all the lakes in New York, whether it's a bloom is confirmed or simply suspicious, or when we've gotten measured high toxins, in all cases over the years, the number of blooms have been increasing across the state. And when we look at the Finger Lakes, Honeoye probably had blooms back in 2012, but the other Finger Lakes did not. We are seeing an increase in blooms, and you're well aware of that again for Owasco, where we know that there are high toxins and have been for several years now, but they did not used to be. So we do have a water quality problem, but it isn't simply that we're getting excess growth from increased phosphorus. Now, my real expertise is in coastal ocean quality, and I've lived in the Finger Lakes for 35 years or so, but I haven't done a tremendous amount of work in the lakes until recently. And it was the bloom in Skaneateles in 2017 that really caught my attention, because again, Skaneateles is a low phosphorus lake, it's a low productivity lake, and in 2017 we suddenly had a big bloom of these toxic cyanobacteria. On top of that, 2017, the spring and early summer were cool and cloudy, and those are not the type of conditions you'd think would lead to an HAB bloom necessarily, as John was saying. So this is a very unusual event. It clearly does not fit this classic paradigm of too much phosphorus just leading to excessive growth and then a bloom. Something else is going on. What might have changed in the years leading up to 2017? And I'd like to suggest we need to look beyond the classic paradigm that we ecologists and water quality managers have relied on for decades. So what's changed? Well, one thing that's changed is the invasive mussel issue, and Kim will talk about that next, and I very much look forward to talking about that. But I think it's entirely possible that the zebra mussels and then the quagga mussels have played a role in encouraging HABs in these lakes. But what I want to talk about myself is nitrogen, and does nitrogen have a view? So let me run through the classic view again of lakes. That is, blooms of cyanobacteria, the blue-green algae, occur mostly in eutrophic lakes, not lakes of lower productivity, and only when the phosphorus is abundant and nitrogen is relatively scarce. And the reason they do this is that these cyanobacteria, some of them have the capacity to take atmospheric nitrogen out of the air and convert it into form they can use. So if phosphorus is abundant and nitrogen is rare, these things have a competitive advantage over other types of phytoplankton, and they'll bloom. We've known that a long time. I and others wrote a review paper on this back in 1988, so this is not new science. That's sort of the classic way we've thought about why and when cyanobacteria occur in lakes. That's not what's going on in Owasco. It's not what's going on in Skaneateles at all. Something else is going on, and what I think might be going on is illustrated in this slide. So we're looking at a space here with various lakes falling along gradients of increasing phosphorus and increasing nitrogen availability. And that classic model I just suggested occurs down here, where the phosphorus is really high and the nitrogen is low, and we get these cyanobacteria that are capable of nitrogen fixation using this molecular nitrogen from the atmosphere. Again, these are not the Finger Lakes with the exception of Honeoye. Honeoye fits this model, but the other Finger Lakes do not. At sort of intermediate phosphorus and intermediate nitrogen, we don't tend to get cyanobacteria at all in lakes. We get other types of phytoplankton, diatoms, green algae. But at very high nitrogen, there's increasing evidence that we get a cyanobacteria for a different reason, and that is that they can take the high amounts of nitrogen and produce the toxins. The toxins, microcystin and other toxins, are very nitrogen rich. So it's not that their growth rate is controlled by phosphorus. Their growth rate is controlled by phosphorus, so let me restate there. But the high nitrogen allows them to produce the toxins. And the toxins are important to these guys. They're not producing toxins in order to poison people, even though that happens. They're producing toxins in order to protect themselves from being grazed by zooplankton and perhaps by the mussels. Now, there's some experimental evidence for this. A recent paper from last year, scientists in Arkansas experimentally took water out of some reservoirs, and they brewed them in tanks for a bit, and they changed the relative amount of nitrogen and phosphorus, and at relatively low quantities of nitrogen compared to phosphorus, the toxin levels were low, but you increase that nitrogen level to nothing else whatsoever to these water samples, and all of a sudden you get a lot of microcystin. So again, that's because the high nitrogen allows these cyanobacteria to produce that toxin. The growth rate here is still controlled by phosphorus. I think I've said all of that, except I want to point out that in a low phosphorus lake like Scandinavialis, these cyanobacteria are probably growing slowly because their productivity is controlled by phosphorus. But you can still bloom, you can get a high abundance even if you're a slow grower, if you're not grazed. And that's where the nitrogen and the toxin aspect comes in. So we actually published a model on this decades ago for coastal waters, but it's applicable to lakes. And whether you get a bloom of cyanobacteria depends on the growth rate, which is a function of phosphorus and light and temperature and mixing and all of the things John was talking about, but also the death rate. And the death rate is in part controlled by whether they're eaten by zooplankton and perhaps by mussels. And nitrogen is playing the key role here. So let's look at some data, and this is out of the latest DEC Finger Lakes report. We're looking across the Finger Lakes from the west to the east. So here's Owasco, Scandinavialis, 2017 data. This is a log scale, so 10 times more toxin here than there, 100 times more here than there. These are really high levels of toxin across these lakes. We're not seeing a lot of toxin in these other lakes. And it may be related to the amount of nitrogen in the lake. So what I'm showing you here is the mean ratio of the total nitrogen to total phosphorus in July of 2017 across these Finger Lakes. And if we look at Owasco, or particularly Scandinavialis, it has proportionately more nitrogen compared to phosphorus than do the other Finger Lakes, and it's up in that range where experimentally it's been demonstrated that it can increase the microcystin concentration. But there are other things going on, and I just want to make sure that we all understand that. According to this DEC report again, these 6 lakes, including the 3 I just showed you, including Owasco, are the lakes that have quagga mussels. So there's whether or not this is simply coincidence that when you have quagga mussels you have higher microcystin, or whether there's some relationship back to nitrogen, I really don't know. But there's something interesting that might be going on. John showed you these data. This is out of his report. We showed them to you already, but I want to just mention again, this is trends in Owasco of the nearshore cyanobacteria over time, 2014 to 18, and the toxin level is going up here. It's going up proportionally to the abundance of the cyanobacteria, and I just want to, I find that very, very concerning if it's a true trend. It is possible, these data suggest there's an increase in the toxin concentration per amount of cyanobacteria in the lake. If that's true, then it could be that the cyanobacteria are evolving so as to better protect themselves from being grazed by zooplankton or perhaps by mussels. We know several people have done excellent work in the Finger Lakes now showing that the zooplankton can evolve to better handle the toxins and therefore actually do better feeding on the cyanobacteria. But cyanobacteria can evolve even faster than zooplankton, and so it could be that the cyanobacteria are trying to keep ahead of that evolution, and this is what we ecologists call an evolutionary arms race. If that's true, it means that we're going to have a harder time trying to control the toxin levels moving forward. Okay, so let me switch from there, and I'm going to talk now about where nitrogen's coming from, what we might do to think about it. I think we want, my conclusion will be that we want to reduce nutrient inputs to these lakes, as John said. We want to reduce phosphorus inputs for sure, but I also think we should reduce nitrogen if any of the arguments I've just made to you are reasonable. So let's see what's going on with nitrogen. Again, this is from the DEC report, and they're looking at the summer average total nitrogen concentration across various Finger Lakes. So each dot here is a different lake. There's Owasco, Cayuga, Scandinavialis, and you can see that if you have a watershed that is more forested, nitrogen tends to be lower. If you have a watershed that has more agricultural in it, again, that's Owasco right there, then you have more total nitrogen. So the watershed's influencing the amount of nitrogen that's in the lake. There's a climate aspect. John talked a lot about climate. I want to show you one other aspect of that, or related aspect. 2016 was an extremely dry year, and for nitrogen, the most mobile form of nitrogen is nitrate. It's very soluble, moves very readily in water. If you have a dry year, it's going to accumulate in the soil as nitrate. And then if you have a wet spring and summer, which we did in 2017, it may have flushed this nitrogen at an unprecedented level. And this variation in climate we're seeing, as John said, is probably driven by climate change. There's a growing interest in the scientific community. So this is the latest newsletter of the American Geophysical Union, EU, and there's a whole article on what happens when we have droughts for long periods of time followed by unusual storm events or wet periods. We had that in the Finger Lakes, and I think it might have been the triggering event for the blooms in Scandinavius. So we can look at the data here, and this is precipitation data from January of 2016 through the end of 2017, monthly amounts. This is the long-term average trend in precipitation from 1979 to 2017. You can see that these months in 2016 were relatively dry, and 2017 is wetter above. If we look not only at the precipitation but the stream flow, the water that's actually leaving the landscape and entering the lakes, this is for Wasco, but you see the same thing in Scandinavius. So we've modeled this stream flow from 2016 to 17. There was no stream flow in the summer of 2016. It was actually low in the spring. Creeks were running dry, so there's no movement of nitrogen. And then you get this very, very wet spring and summer in 2017. It's cold, wet time. That's flushing all of the nitrogen, and we think that might be the first trigger for Scandinavius bloom. And again, with further climate change, this sort of oscillation in meteorology seems likely to become more common. Okay, I want to spend just a little bit of time talking about why it matters that nitrogen may play a role here, because after all, nutrients, we're going to control nutrients. Who cares if it's nitrogen or phosphorus? The reason we care is that nitrogen and phosphorus move differently in the environment, and therefore dust management practices are different for the two. And if we're not paying attention to that, we're not doing a good enough job to capture nitrogen. So for nitrogen, it moves readily in drainage waters, through drainage tiles, through streams, it dissolved forms in water. It's got an atmospheric component where ammonia gas goes off to the atmosphere. There's relatively little nitrogen that's moving with eroded soil. For phosphorus, it's quite different. There tends to be very little in drainage, with an exception I'll come to in a bit. The phosphorus problem is largely one of erosion, movement of soil, movement of sediments. The phosphorus is stuck onto the sediment. That's a big difference. I do want to say that it's possible, if you put too much phosphorus onto the landscape, you can add so much that the phosphorus is no longer completely sticking to the soil, and it will start to move in water-soluble forms as inorganic phosphate. If that happens, then phosphorus behaves less like this and more like nitrogen. So either way, we need to pay attention to best management practices which deal with nutrient flows in water and not simply an erosional aspect. So, what do we know about best management practices? If we look at some very common practices and see how effective they are for either phosphorus control or nitrogen, and here I mean phosphorus at levels which have not yet saturated that ability to no longer stick to the soil and move in water. No-till agriculture is a very popular way to control phosphorus. That's because it reduces soil erosion, and if you reduce soil erosion, you reduce the movement of phosphorus. It's not effective at all for nitrogen, and in fact there are several studies showing that when you go to no-till agriculture, you aggravate the problem of leaking nitrogen to downstream streams and lakes. Buffer strips are also really nice for phosphorus because, again, you're dealing with erosion. You're capturing the eroded soil rather than letting it get into your streams and lakes. That works for nitrogen sometimes, sometimes not. You have to actually capture the nitrogen that's in the flowing water in groundwater, not simply erosion, if it's to work. Better things for nitrogen are things like winter cover crops and switching away from corn towards perennial grasses and things like that, which are much more effective at keeping nitrogen in your fields. And I want to emphasize this because I think it has a lot of potential in this area. A lot of the agricultural fields in this area are tile drained. John showed a nice picture of a pipe coming out, hitting into a ditch. A lot of the nitrogen and phosphorus, if the soil saturation of phosphorus is occurring, is moving in these drainage tiles. It's draining down through the soil. It's coming up through these pipes into these ditches and then very quickly into a stream, into your lake. It's possible to manage these drainage systems, manage the water flow in them, which also manages the nutrient flow. This is increasingly done in the Midwest and Illinois, not so much in New York, but the Department of Agriculture is promoting it now heavily in New York, and I really think we should be looking at it in the Finger Lakes. It's a great way to have less nitrogen and less soluble phosphorus leaving these fields. Just a little bit more on the atmospheric aspect, because again, phosphorus doesn't tend to move through the air as a nutrient, but nitrogen does as ammonia gas, and when you spread manure like this and don't plow it into the ground or inject it, there can be a lot of ammonia gas coming off to the air. You'll smell that, but the smell is not just a nuisance smell, it's moving nitrogen through the landscape. It's a public health issue, but it's also a water quality issue. And we have some data on exactly how far that ammonia can move. We measured ammonia concentrations near Cornell's experimental farm down in Hartford, and within a kilometer or so either side of the farm, you get very high levels of ammonia gas in the atmosphere, and still elevated up to several kilometers, so several miles away. And what that means is that you need to start thinking about protecting the airshed of a lake and not simply its watershed, because you could be pumping nitrogen from other watersheds into your watershed through this atmospheric transport. So here are the prevailing winds are this way, and for Scandanalysis in particular, if you have animal agriculture in this way, it's going to influence Scandanalysis, and that's obvious, right? One other aspect I just want to note is that there has been an intensification in animal agriculture in the region over time. So these are data for Cayuga County. We're estimating the amount of nitrogen that's excreted from livestock over time from 87 up to 2012. We don't yet have the 2017 data. This is based on Department of Agriculture National Survey of Agriculture, which happens every 5 years, and they haven't released the data yet. But you can see there's been an increase in the nitrogen that's excreted. There's more animal agriculture, more phosphorus, more potential for saturating the soils and moving phosphorus in water as well. So my conclusion is we don't know that nitrogen's playing a role here in these blooms, but I think it may well. We do know that the classic model of phosphorus being the only thing which matters is unlikely to be the case in these lakes. Something else is going on, perhaps the mussels, which I'm looking very much forward to hearing Kim talk about in a minute. But my fundamental conclusion is that for all aquatic systems, certainly coastal systems, but freshwater lakes as well, we really need to control both phosphorus and nitrogen. This is from a paper we published 10 years ago making that argument, and I think it's time to get on that. And again, recognize that it requires different management practices and explicit attention to what those management practices might be. So that's my talk. Thanks for the chance to talk to you. I just want to thank the Atkinson Center at Cornell, which is funding our work. I didn't show you much data because we've actually only been working on this for about 6 months, but within the next few months I hope to be able to tell you much more explicitly what climate might be doing to this movement of nitrogen and phosphorus. And I also want to thank these colleagues at Cornell, including Roxanne Marina, who is in the audience right there today. So, thank you very much.
A few questions there. You indicate that nitrogen is influencing algal blooms. However, the total nitrogen trend in Cayuga Lake is known to be stable or even falling over time. Do you have any nitrogen data from Owasco to support your idea?
That's a great question. The trends on total nitrogen, well, let me give a couple of answers. I think the long-term data on total nitrogen are problematic. Total nitrogen is analytically much more challenging to measure than is phosphorus and some other nutrients, and slight methodological differences result in giving you different numbers. And so unless you have careful lab-to-lab intercomparisons and comparisons of methodology over time, we don't have reliable data over time. And that has not happened with total nitrogen in any of the Finger Lakes. So we have data over time, but long-term trends, I think, are questionable. So that's one answer. The second answer is that it may not be the total nitrogen that matters, it might be particular forms. Nitrate has been going up in some of the lakes, down in other lakes. We know that better because nitrate's easier to measure than total nitrogen. But it could be that the specific form, ammonia, or perhaps even urea might be more important than nitrate. We don't know. That's something that I think we should be looking at. And then it may be that the lake averages or the total lake averages, the mid water column sampling points aren't the places we want to be looking. We might be wanting to look in those near-shore areas that John highlighted so much in his talk as the place where the blooms might be originating.
Okay, another question. If soils within septic leach fields of nearshore septic systems are saturated for phosphorus, does this phosphorus become water soluble and easily move into the lake water?
The answer is yes. If the soils become saturated with phosphorus, it will move. Two things on septics and septic tanks and septic fields. If it's well designed and well maintained, the leach field is supposed to prevent the soil from becoming saturated with phosphorus, so it shouldn't happen. But if it's not adequately maintained, or if it's more waterlogged than one would want by design standards, that becomes much more problematic. Also, septic tanks are designed to try and hold on to phosphorus as well as bacteria. That's their role. They're not designed to hold on to nitrogen, the terrible nitrogen. Nitrogen just flows out of them with about a 95% efficiency. So they're a big source of nitrogen in these near-shore lakes. Jim.
Yes, I have a question here for Dr. Howard. Suggests that nitrogen is driving algae blooms with what N sampling data do you have to support this concept? What is the 10-year trend for nitrogen on Owasco Lake?
Yeah, well, that relates to the first question. To begin with, I should say that in my lab, we have not sampled for nutrients at all in the Finger Lakes. So the data we're looking at, the data we're using in our analysis are coming from the citizen surveys, the DEC, the CSI effort for Cayuga Lake, and health data. In terms of trends long-term for total nitrogen, again, I don't think that they're reliable data there. And for two reasons. I don't mean that as a type of criticism. The focus has been on looking at things like chlorophyll and oxygen, the sort of lake responders, and on phosphorus, which is what any of us would think is driving the overall phytoplankton growth, and what I, too, up until a few years ago, would have said is by far the prime and only problem in these lakes. So the idea that nitrogen may have this contributing role because of the microcystin aspect is a new idea, and that means that the people who've been doing monitoring have not been focusing on nitrogen. To the extent they've done it at all, it's sort of a nice add. It hasn't been a prime focus. And with that in mind, measuring total nitrogen is difficult, and so the long-term data I don't think are robust.
Yeah, I do two more questions before we take a short break to keep on our schedule. If nitrogen in the air is a problem and animal agriculture is part of the blame for that, why would the Aurora Cornell Research Station show a 30% reduction in nitrogen deposition since 2000?
The deposition that's measured at Aurora is oxidized nitrogen. It does not include dry deposition of ammonia gas, is answer number one. Answer number two is that the overall wet deposition that they measure and is also measured throughout the Northeast in the NADP, the National Atmospheric Deposition Program, is picking up on the effectiveness of the Clean Air Act. We're putting a lot less nitrogen into the atmosphere, particularly from vehicles, but also from coal-powered power plants and natural gas-powered power plants, the amount of nitrogen that's going into the atmosphere now is about 10% of what it was 20 to 30 years ago, and it shows up in the deposition. We have less acid rain, we have less nitrogen pollution overall. But the ammonia levels, contrary to that, where it's measured in the NADP, including our station in Connecticut Forest and Tompkins County, have been going up.
Okay, one more for now before. Could you repeat the nitrogen tiling remediation ideas?
Yeah, the idea is that instead of just letting the water run straight through your drain tile and into the stream, you have an ability to, a gate, if you will, so you can regulate the flooding of the fields and the time and amount in which it comes up. So at the time of spring melt, which we all hope will be tomorrow or next week, but soon, you know, at the moment, these soils are incredibly rich in nitrate. And they're frozen, but the minute that melts, you can have an incredible amount of water moving through these drainage systems. It's very nitrate rich. If you can hold it in the field longer until the fields start to just dry from evaporation, then you're not moving it to the lake. And the Department of Agriculture has recognized this as one of the most effective ways to deal with nitrogen pollution, so they are actively promoting it. Again, throughout the Mississippi River Basin, they've started to promote it in New York. As far as I know, it's not common practice here in New York, but they will help pay for it. They argue strongly that it increases farm crop productivity as well as helping with water quality. So I really want to emphasize that's something that we should be looking at.
Add to that, I mentioned earlier the DeMond property on Van Ness Brook. They're installing a two-stage system for drainage that will hold back the water and allow it to be absorbed better and not.
Yeah, looking at drainage. John made this point too, but you know, drainage is a big aspect of the problem here. The more we can do to think creatively about the drainage issue in a way that is good for the farmers as well as good for the lake, it's a win-win.
Thank you, Dr. Bob.
Thank you.
I want to take a short break for 10 minutes to give you. We'll be back with the. Still have go. Get all that? We're in Syracuse.
If we could touch base.